Okay, so in this session we'll take up the Towers experiment in the third module of hydrodynamic journal bearing. So Towers experiment started in the earlier 19th century, where at that point of time people used to think that there will be direct contact between the journal or the shaft and the bearing exists. So people used to think there will be a contact between journal and the bearing, and to reduce the friction between the journal and the bearing, we need to supply the oil. This was the mentality of the people at the 19th century, at the beginning of the 19th century. So just to make the surface between the journal and the bearing slippery, to avoid friction, to reduce friction, people used to supply the lubrication. That is what the concept was there in the earlier 19th century. So in the earlier 19th century, Tower observed that when the journal is running inside the bearing, he observed some of the oil spilling out of the bearing part. So he started thinking, why this oil from the assembly spilling out of the bearing. He has just thinking, and he has coming to the conclusion to conduct certain experiment to know what could be the reason between the spilling of the oil from the journal and the bearing. So he has decided to conduct the experiment. For his experiment, he has taken the journal of dimension 6 inches in length and 4 inches in the diameter, then introduced a journal. So this is the bearing part and this is the journal part. In the side view it is something like this, with the bearing part and the journal part. The part of the shaft inside the bearing is called as journal. Okay, so this is what the side view of the journal bearing assembly. Okay, in the first experiment, Tower has made grooves, parallel to the axis of the shaft, something like this. Okay, Tower had made grooves parallel to the axis of the shaft, something like this, and he has supplied the lubricant through that groove. Okay, he has made the groove parallel to the axis of the shaft and he has supplied the lubricant, and he has analyzed the behavior. So this experiment doesn't yield a good performance of the lubrication. It is not satisfactory. The result was not satisfactory. Then he has made the groove as curvy, not parallel to the axis. He has made the groove as some curves. Then he has again introduced the lubricant, again tested for the performance of the lubrication. Again it doesn't yield good result. This is the first set of experiment. So in his second set of experiment, the Tower introduced some pad which contained an oil bath of the lubricant. He has kept certain pad here, something like this. He has kept the pad which contained the oil bath. Okay, and he is going to conduct the experiment by running the journal. Now in this case, when the journal is running, there will be a rubbing of the journal with the pad. Thereby there will be a capillary action, there will be a suction. Due to that capillary action, the oil in the pad is going to spill out and it will act as the lubrication. This was the second set of experiment. So he has kept some pad containing the lubrication below the surface of the journal. Then when the journal is rotating, it is going to rub, the journal surface is going to rub the surface of the pad where the capillary action is going to take place. Due to that capillary action, due to the suction, the oil spills out from the pad and it will be distributed. Okay, again this experiment doesn't yield good result, good performance of the lubrication. This is also not satisfactory. So in the next set of experiment, he has immersed the assembly of bearing and the journal in an oil bath, something like this. He has taken an oil bath, he has immersed it, then again he has conducted the experiment. So this set of experiments given him a satisfactory journal bearing performance. Okay, this yields good results or the better performance. Okay, now at the middle of the experiment, he has taken this assembly out of the oil bath and he has made an and he has made an hole in the bearing. Fine. Then he has introduced again in the oil bath and he has observed the working of the journal now. So when he observed, the oil is again started to spill out of the hole. Okay. So at the middle of this experiment, he has taken the journal bearing assembly out. He has made an hole. Then again he has introduced in the bath and started running the journal. Then because of some pressure developed, the oil spill out of the hole. This is what he observed in his next experiment, next set of experiment. So with these set of experiment, he has concluded that the oil film between the journal and the bearing, will have some load carrying capacity, because of the pressure developed in the oil film. Okay. So he has concluded that there will be pressure developed in the oil film in between the journal and the bearing, and that pressure in the oil film can carry the load of the journal. This is what the conclusion from the Tower. So in the earlier 19th century, people used to think that we need to supply lubrication in between the journal and the bearing just to avoid the friction and to make the surface slippery. But Towers concluded that there will be pressure development in pressure distribution in the oil film. That pressure can able to sustain some amount of load of the journal. So load carrying capacity of the oil film was given by the Towers experiment. Okay. So this is about the Towers experiment. Next, the Reynolds, one more engineer, has started working on the Towers experiment. Then he has concluded with the Towers experiment the load carrying capacity and the pressure distribution in the oil film like that. He has derived certain equation which contains some partial differentiation to explain the result of the Tower. Okay. So Reynolds given the equation to explain the Towers experiment in terms of partial differential equation, where we can know that the pressure distribution in the oil film depends on what parameters. Okay, so these are all the Reynolds investigation on the Towers experiment. So the Reynolds show the importance of viscosity of a lubricant on the frictional characteristics and load carrying capacity of the journal. Then Reynolds again showed the importance of bearing clearance. Then he showed analytically. So analytically means with the help of some equations, he has showed analytically that the lubricant which adheres to the surface of both moving and the stationary, that is journal as well as the bearing surface of the bearing surface, develops a positive fluid pressure. So Tower has conducted certain experiment and he has concluded that there will be pressure distribution in the oil film between the journal and the bearing. But Reynolds continued the discussion or continued the study, and he has given some analytical equation to justify the pressure distribution in the gap between journal and the bearing in the oil film. That is for the investigation of the Reynolds. Again, that fluid pressure developed in the oil film can able to withstand the load, can able to sustain some amount of load, and it can help to prevent the contact, direct contact between the journal and the bearing. This is what one of the observation of the Reynolds. Then he derived a differential equation for the pressure distribution in an oil film. So this differential equation becomes the basic equation for the hydrodynamic lubrication. So if you talk about hydrodynamic lubrication, the basic equation stands as Reynolds equation for the hydrodynamic lubrication. So with that equation, Reynolds concluded the experiments of the Tower. So these are all the assumptions made in the Reynolds equation, because any derivation starts with the assumptions. Therefore, these are all the assumptions made in the Reynolds equation. The first assumption is the motion of the fluid in the film is laminar. He has considered the laminar, he has assumed that the flow is laminar. Then he has assumed that the fluid is incompressible. Then the fluid he has assumed which obeys the Newton's law of viscosity. Then the viscosity of the lubricant remains constant throughout the oil film. This is what another assumption. Then there is no end leakage. That means to say, if you consider the motion along horizontal direction like this, so there is no motion in the perpendicular direction. This is what the assumption. So you need to consider the length of horizontal direction as infinity, so that the flow in that direction is neglected. This is another assumption. Then there is no slip occurs between the lubricant and the bearing surface. Then the next assumption is the clearance between the journal and the bearing is small, both clearance as well as inertia force. Okay, is assumed to be small. Thereby the effect of those clearance and the inertia force can be neglected. So these are all some of the assumptions made by the Reynolds to come up with the equation, Reynolds equation, which specifies the pressure distribution in an hydrodynamic journal bearing. So the Reynolds equation, for the derivation of the Reynolds equation, he has considered the case 3 type of the plates, where he has considered surface A, which is parallel, and surface B, this is surface B. Okay. So this is not parallel. One is inclined and another one is parallel. This is the third type of the flow. So in this type of flow, he has considered one small elemental fluid. Okay, small elemental fluid. The load is applied perpendicular to the plate. The velocity is considered as u, and the coordinates considered here is x in this direction, in the horizontal direction, y in the perpendicular direction like this, and z in the perpendicular direction to the board. The corresponding velocity in the x direction is considered as u. The corresponding velocity in the y direction is considered as v, and the corresponding velocity in the z direction is considered as w. Okay. So a plate horizontal, plate A, and an inclined plate B, the flow in between the plate given rise to velocity as well as the pressure distribution. So in that particular type of flow, a small elemental fluid is considered, and the pressure distribution is written here. Look at here, this is the magnification. This is the magnification of this small elemental fluid, this one. So ultimately our agenda is to apply equilibrium equation. So an engineering material should be in the equilibrium. Okay, so we need to apply equilibrium equation. Equilibrium equation start with the forces. Equilibrium equation, you are going to write the equilibrium equation for the forces, summation all the forces in x direction equal to 0, algebraic sum of all the forces in y direction equal to 0. Okay, so we have the force in the equilibrium equation, but whenever the fluid is whenever the fluid is there, then the object inside the fluid will experience the pressure. Okay, whenever the fluid is included, the object inside the fluid experience the pressure. So we need to convert that pressure into the force to apply in the equilibrium equation. So how to convert pressure to the force? We know that pressure is nothing but force by area. We know that pressure is nothing but force by area. So multiply area with the pressure, you can get the force. So force is pressure into area. This we know from the basic understanding. Okay, that is what did here. So a small elemental fluid is considered of length dx in x direction and dx in z direction and dy in the y direction. Okay, so at the left part, the force is considered as P into dy dz. Here the P is the pressure and dy into dz is the area, this amount of area. Dy into dz, this amount of area, the left face. And in the right hand side, P plus dp by dx into dx into dy dx. So here dy dx dz, dy dz is the area, it is multiplied with pressure, this is the amount of pressure. So why this term is included here, differentiation, because the pressure P in this position will not be the same in this position because of the length dx. As the length increases, the pressure may vary. Okay, therefore I have introduced some variation of pressure with respect to the length dx. This is the variation of pressure with respect to the dx. So P at this surface plus the variation of pressure because of the distance dx is included here. This is the pressure at the right hand surface multiplied with dy into dz is the area, you will get the pressure force. To obtain the force, I have multiplied pressure with the area. Similarly at the top surface, but at this surface it will be shear. Okay, so if I consider element something like this, it will be under hydrostatic pressure entire. So pressure into the area gives you the force. So this is the left hand surface where we need to consider this amount of area, this into this is the area we are considered. So dy, this is dy into dz, dy into dz, dy into dz, dy into dz, this is the area, this. Then at this particular position, pressure will not be same because of some length, because of the length. So variation of pressure because of the length is considered, fine. Okay, but at the top surface and the bottom surface, since the fluid is flowing like this, there will be shear, okay, that shear stress is considered like this, shear stress into dy dx into dz. Again dx into dz is the area, this amount of area, dx and dz, this is the area on which this shear stress is acting because of the flow. So to get the force, I need to multiply area with the stress to get the force. So this is the force, stress into area is the force. Similarly, tau plus d tau x by dy, this is to account for the variation of shear stress from top surface to bottom surface, because from top surface to bottom surface there is some length of dy, there will be some variation of shear stress. Therefore, to account for the variation of shear stress through the length dy, I have introduced, the Reynolds has introduced this term. So tau plus d tau by dy into dy is equal to dx into dx dy is not is equal to into dx dy. So this is the area and this is the shear stress at the bottom surface. That is what considered here. So the forces acting on the elemental length, the pressure force on the left hand side is considered as P into dy dx on the right hand side, so and so. Then shear force on the top, so and so, and the shear force on the bottom, so and so. Again, consider these forces, apply equilibrium equation. So applying equilibrium equation, considering sum of algebraic sum of all the forces in x direction equal to 0. So consider equilibrium equation on the elemental fluid like this. P P into dy dz, only horizontal force you need to consider, P into dy dz minus this one because it is opposite in direction, P and P plus dP by dx opposite in direction, so minus plus tau in this side and tau it is opposite here and top as well as bottom. So tau, one is positive, another one is negative, that should be equal to 0. So algebraic sum of all the forces should be equal to 0. So if you simplify this one, if you multiply this term P into this, P into dy dx minus P into dy dx, cancel with this one. Similarly, minus tau x into dx dy, it will be cancelling with this one. Then dx dy dz, dx dy dz, that will be the volume, that will also going to cancel if you simplify this. So if you apply some simple mathematics to simplify this equation, you will end up with dp by dx is equal to minus d tau x by dy. Consider this equation as 1. So dp by dx is equal to minus d tau x by dy. I will call this equation as 1. I will start with this one now. So according to Newton's law of viscosity, we know that tau, the shear stress, is equal to nu into du by dy. Okay. But here if you observe, as y increases from this point to this point, the velocity is going to decrease. Something like this. We can have a look at the velocity distribution. It will be something like this. So as y decreases, the velocity is decreasing. So velocity is maximum at the moving surface and minimum at the stationary surface. So as y increases, velocity decreases. Since this is happening, I am going to consider negative. In this equation, I am going to consider negative. Okay, this equation is written for the upward motion. This equation is written for the downward one, considering the downward one. Okay, so minus. So substitute this one, minus eta into du by dy. In this, you will get dp by dx is equal to this one, dp by dx is equal to d by dy of tau. Tau I will substitute this one here. So upon simplifying, you will get and rearranging, simplifying and rearranging, taking d square u by dx square to the left hand side, d square u by dy square is equal to 1 divided by eta into dp by dx. I will call this equation as 3. Then integrating with respect to y, integrate this term with respect to y, you need to double integrate it because square term is there. So du by dy is equal to first differentiation. So differentiation of this with respect to dy. So if you differentiate, you will get a c1 term as well as c2 term if you differentiate twice. So after this one differentiation, you will get u is equal to 1 by 2 eta into dp by dx into y square plus c1 into y plus c2. I will call this equation as 4. This is after different integration of this particular equation. Integrating the equation 3, you will get equation 4. So in equation 4, C1 and C2 are the integration constants. Integration constant that needs to be obtained by applying the boundary condition. Okay. So because this equation we end up by considering a small elemental fluid, this one, we end up with some constant. This constant we can obtain by applying the boundary condition. So the boundary conditions are at y is equal to 0, u is u, at y is equal to h, u is again 0. That means to say at y is equal to the first boundary condition, at y is equal to 0. Y0 means moving surface, this one, y0. Of course, at the moving surface the velocity is u. It is written here, velocity is u. Similarly, at y is equal to h, h means this one. At y is equal to h means it is the surface which is stationary, u is 0. So this distance is h. At y is equal to 0, velocity is u. At y is equal to h, velocity is 0. U is 0. So if we substitute both the boundary condition, what will happen? if I apply the first boundary condition, from the first boundary condition, y is equal to 0, u is equal to u. If I apply this one here, y is 0. So apply 0 here. This term will be 0 if you apply 0 here. Then substitute for y is equal to 0 here. Again this term is going to be 0. These two is going to be 0. Therefore C2 is equal to u. You will come across C2 is equal to u if you substitute the first boundary condition. Then applying the second boundary condition, y is equal to h, u is equal to 0. Apply the second boundary condition. So y is h, substitute in the place of y, h, y becomes h square, that is what written here. Then here C1 into h, in the place of y substitute h, written here. Then C2, C2 from the first boundary condition I know that C2 is equal to u, so I have written in place of C2 u. Therefore this is from the second boundary condition. Applying the second boundary condition, replacing y with h and u with C2, C2 with u. Okay, I obtained this one. So from this I need to get C1 because I have already got C2 by applying the first boundary condition. By applying the second boundary condition you need to get C1. Therefore I will take C1 term in the left hand side. So if I take C1 term in the left hand side, the right hand side it will be minus 1 by 2 nu dp by dx p h square minus u. So I have taken this term to left hand side and this term to right hand side, something like this. So rearrangement of equation. So again sending h to the right hand side because I need only C1 to substitute back in this equation. So C1 is equal to, taking h to the right hand side, you will get the equation something like this. Now substitute C2 and C1 constants in the equation 4. In the equation 4, you will get C1, substituting C1 and C2 in the equation 4, you will get something like this. And if you simplify this, you will get u is equal to so and so, an expression which is having two terms in the right hand side, the first term plus the second term. Okay, so this is in the form of u is equal to u1 plus u2, u1 plus u2, where u1 will be is equal to the first term 1 by 2 nu into dp by dx into y square minus hy, the first term, and u2 is equal to u into the second term. Okay, so I will get velocity of the moving plate as two terms. The first term will be indicating the parabolic velocity distribution, this one, because there is a pressure gradient and all. So it indicates the parabolic velocity distribution. u2 indicates the linear velocity distribution. Look at here, by looking at the equation you can conclude that u2 will be having linear velocity distribution and u1 will be having parabolic velocity distribution. So this equation I will call it as equation number 5. Equation number 5. If you observe equation number 5 carefully, equation number 5 in the left hand side it contains the velocity of the oil film. In the right hand side it contains the viscosity, the pressure gradient, then y term, h term, again the velocity at the moving surface. Okay, so here h is constant because once you select the width h, it will be constant. So in equation 5 gives you the velocity distribution at any point, at any section. Y, you can substitute any value of y. Like if you want velocity at this position, substitute y as this one. If you want velocity at this position, substitute y is equal to this amount. Likewise, in any layer, okay, if you substitute that particular y distance, you will get the velocity at that particular location, at that particular layer. This is what the beauty of equation number 5. So equation number 5 determines the velocity distribution at any point in the said figure, in the said orientation, like this. Okay. So the first term u1 represents the parabolic velocity distribution It is because of the pressure induced flow because of the orientation. Okay. So the first term U1 is depends on the pressure gradient dP by dx, pressure gradient. So if I apply some conditions, boundary conditions at y is equal to 0, if I apply y is equal to 0 at the moving surface, y is 0. If y is 0, then this term will be 0. So entire time U1 also be equal to 0 if you substitute y 0. Similarly, at y is equal to h, if you substitute y is equal to h, if you substitute y is equal to h into h square, y square means h square minus h square cancels, again this term will be equal to 0. So U1 will be 0 at this surface as well as 0 at this surface. U1 will be 0 at the moving surface as well as 0 at the inclined surface which is stationary. Therefore, you need to define U1 in between. So considering y is equal to h by 2, y is h by 2, U1 is equal to, substitute in the place of y h by 2, so h square by 4, 2 square 4 minus h square by 2. This is h by 2, so h into h square divided by 2. If you simplify, you will get U1 is equal to minus h square by 8 eta into dP by dx. So U1 depends on the viscosity of the oil considered, then the height and the pressure gradient. So this is the represents the parabolic velocity distribution. Next, U2 is the linear velocity distribution because U2 is equal to U into 1 minus h by y, which represents the linear velocity distribution of the oil film. Since the fluid is assumed to be incompressible, the volume of fluid into the space should be is equal to volume of fluid moving out of the space. So this is what the convention we need to consider. Therefore, Q into the space should be is equal to Q out of the space. So Q into the space, U into dy dz plus V into dx dz plus W into dx dy. So as I said earlier, U, V and W are the velocity in 3 different directions, x, y and z. That is what this thing is equal to U plus du by dx into dx. So here the second term du by dx into dx is the variation of the velocity because of the distance dx. So velocity will not be same at 2 different positions. So if at the left hand end it is u, in the right hand end it should be u plus du by dx into dx. Because of the distance, the variation should be considered. This is the variation considered here multiplied with this one. The same thing happens with v as well as w. So dv by dy into dy will be the variation of velocity along the distance dy. Similarly, dw by dz into dz will be the variation of velocity along the distance dw. So this is the equation, q in is equal to q out. So the term u1 represents the parabolic velocity distribution and u2 represents the linear velocity distribution, and the volume of flow into the space and out of the space should be equal. Therefore, we can write this equation. So after simplification of this particular equation, you will end up with this one. Since the flow in the z direction is neglected because we are deriving Reynolds equation for 2-dimensional one. So since the direction in the z direction is neglected, we can neglect deva w by deva z, that will be equal to 0. Therefore, this equation again reduces to this 2-dimensional, only u and v term will be there. Again, substituting the values of u from equation 5 here in this. So equation, you can call this equation as equation number 5a, where you can take this particular term to the other side. So deva u by deva x will be equal to minus deva v by deva y. Substitute for u from equation 5, you will get deva v by deva y is equal to minus deva by deva x of u term. This is u term, where this is u1 and this is u2. this represents the parabolic velocity distribution, and this represents the linear velocity distribution. So this is u term dy by x of u, and here since the velocity v is equal to 0, when we consider the boundary condition when y is equal to 0 and y is equal to h. So y is equal to 0 means it is the moving plate on which the velocity will be 0 u1, as well as at h, at the stationary plate again the velocity will be 0. Since the velocity is 0 when y is equal to 0 and y is equal to h, integration of 0 to v between the limit 0 to h dv by dy will be is equal to 0. If I apply this condition to this equation, equation number 5, and if you integrate equation number 6, sorry, it is equation number 6, if you integrate equation number 6 by considering the limit 0 to h, and on simplification you will find this equation d by dx of h cube dp by dx, which is pressure gradient, is equal to 6 into the viscosity of the fluid multiplied by the velocity into dh by dx. So you can still simplify this equation, but for the academic purpose this much is enough. So this you can call it as Reynolds equation in 2 dimension.